All right, so here we are. We're continuing with looking at complex numbers, and wait, should that be on that side or on the other side? I'm not too sure. Anyway, and my face is like this because of temperatures. The temperature sort of messes up with my face. Oh, I get it. I was writing on a white paper with a white pen. Anyway, all right. This is just where I take notes. Not into the problem solving section yet. I'm still just reading through the material. So last time we saw this piece of notation, cis alpha, and I believe that this was cosine alpha plus I sine alpha. And we learned about a complex number, which in general is something of the form a plus bi. I meaning the square root of -1, and a and b both being reals. And we also learned that z bar or z star is the conjugate of the complex number z, and that would be a minus bi. We learned how to do addition, subtraction, multiplication, and division of complex numbers. And so now we're looking at properties regarding the modulus and the conjugation operation, and also the taking the argument of a complex number. All right, so I need to remind myself what it means to take the modulus of a complex number. Well, that would be the square root of a squared of b squared, and it corresponds to our idea about the overall size of the complex number, the distance that it is from the origin on the complex plane, which is this construction where purely real numbers lie on the horizontal axis and purely imaginary numbers lie on the vertical axis, and proper complex numbers, which have a non-zero real part and a non-zero imaginary part, are in one of these four quadrants here. And there at the origin is the number zero. And so we're talking about this, the direct distance away that the complex number is from the origin. That's the modulus of it. Okay, and what was the argument of a complex number? Arg z. Well, that's trying to get this angle here. I want to say theta, but presumably they would say alpha. And what actually is that? Well, that would be the arctangent of the imaginary part of z over the real part of z, like that. Okay, so with that minor review, now we have to look at proposition 18, which is a collection of 12 mini propositions. And All right, so what does it say here? It says that the modulus of a product is the product of moduli, the moduli of these complex numbers. The modulus of zw is the of z times w is the modulus of z times the modulus of w. It's that beautiful, what do you call it, morphism property that I've encountered before, many times before. All right, so how am I going to sort of think about this one? Well, by definition, we'll think about what the definition of the modulus of their product is. Okay, so first let's say that z is a plus bi and w is c plus di. And then let's multiply them together and see what that looks like. So what actually is that? Okay, so the real part is AC minus BD. And then the imaginary part is AD plus BC. Wait, hold on just a second now. Yeah, that seems okay. And so the modulus of that product will be the square of the real part plus the square of the imaginary part, and all of that square rooted. Okay, so it should be this. Now, okay, so now we have that. Let's consider what the right-hand side looks like. So the modulus of z is this, and the modulus of w is this, like that. But then you have to actually multiply these two moduli together. But remember that when you multiply the square root of something by the square root of something else, you get the square root of their product. Like, well, let's say like 36 and 9. That's going to give you... Oh, wait, did I do this right? Yeah, that's actually fine. 324. Okay, so that's 6, that's 3, and that's 18. And that all works out. So that's all fine. Okay, so now let's just apply that property right here. Mod z times mod w should be big square root sign a squared at b squared times c squared at d squared. Right? That should be the case. Shouldn't it? All right, let's see here. Hope I don't mess this up. No, it looks okay. All right, so somehow that is equal to that. Don't really know how yet. probably, maybe I have to like expand it out. Maybe. Don't know. I'll just try it. Okay, so let's see. We'll get okay, this one, and then this one, and then this one. And oh, look at that. These guys cancel each other out, which is very nice. And so now, let's just say that it's a squared c squared plus b squared d squared plus a squared d squared plus b squared c squared. Okay, so that's starting to look more true. Okay, and then let's expand this one out. Just do FOIL on this. A squared c squared plus b squared c squared plus a squared d squared plus b squared d squared. Oh, and look, you can see that their parts match up. So we can just call that 1, call that 2, and say 1 is equal to 2, which is great. Okay. Now, how can I do number 10 without doing a whole bunch of what I just did? You know what? Let's do this. Let's consider what the reciprocal of W looks like. What does 1 over W actually look like? Because I don't quite know right now. So it's that. And then we'll do this. Top and bottom times it by the conjugate. And then what do we get? C squared minus D squared by design, and then C minus DI on the top. Okay, that doesn't help us a whole bunch, but I think it would just be a lot of algebra, but hey, that doesn't bother me. Let's actually see how they did the 9th one. Okay, so kind of similar. And they just went straight from left to right. Okay, so I'm going to try proving the 10th one then. Let's see. Just feel like this will be very large. Z over W is A plus BI over C plus DI. And so you do top and bottom times C minus DI, like that. Minus AD. BC minus AD. I, just there like that. And then C squared minus D squared. And the modulus of this it's going to look very big and complicated, won't it? Like even in the compressed form, that's going to look big. Mm-hmm. Mm. Well, that denominator there will be squared, won't it? And so will that one. And then we combine them. And then you take the square root of that denominator. And so it's all over C squared minus D squared. You know? So it's really just the top. And that will be that. Won't it? So anyway, that's what the left side looks like. Now I'm going to try the right side. That, isn't it? Wow, that doesn't look the same at all. Well, how do you do it then? Oh, I know. Di times minus di is minus d squared I squared, which is plus. So that's wrong. There we go. That was really important. And let's see, did I get this wrong as well? Yes. That makes sense. Okay. All right. And when now maybe like this square root sign is actually meant to be there, and I dropped that as well. So what I'm going to do is I'm going to investigate what's underneath that square root sign there. So we get a squared c plus 2a minus 2a squared b squared plus a squared d squared, like that, and then these cancel out like before, don't they? So you get this. Which is what's from earlier, isn't it? Yeah, it's this. A squared of b squared times c squared of d squared. Right, so obviously these aren't the same thing, and this is just complete rubbish. Or is it? Yeah, wow. Maybe I got this totally wrong. Okay, AC minus B AC plus BD BC. Yeah. And all of that has, you have to get the real part of that. So that there is squared. That's the real part. And then you square it. And that's the imaginary part. And then you square it. And then you have to add them together. Yep, don't know. So that right now is this. And that right now is this. Are these the same? No, they can't be. Or can they be? Okay, so that one there, of course I can turn it into that. Can't I? And then this one over here, same story. Okay, so times the top and the bottom by the square root of c squared or d squared. All right, and then they're equal. Okay, so I'm convinced. Right, what about this one? The argument of zw is the same thing as the argument of z plus the argument of w. Okay. The argument of a at bi is the, by definition, it's the arctangent of b over a, isn't it? Okay, so a at bi times c at di. Then figure out the product. Come on. What is it? There. No. Minus BD. AD plus BC. That's the left side. And yeah, I have no idea how to add a pair of arctangents of whatevers. So there has to be a different approach. And I can see that they're using cis. An alternative form. Okay, so I need to get it into my mind that a complex number does not have just one form. This is like rectangular form, a plus bi, real and imaginary part. But then it also has polar form. But I don't know exactly what that is yet. Something like, what was it? Okay, so it was this. Okay. Can be this, which is what my mind is defaulting to right now. but I need to also remember that it can be this. That's the modulus, and that's the argument of it. And this can be abbreviated to this. All right, so now try again. So what am I trying to prove? I'm trying to prove that the argument of the product of ZW is the sum of the arguments of Z and W. Okay, so first, let's have Z be R cos alpha, and W, well, I want to use S, but that's going to confuse. Whoa, hold on just a minute now. I meant to say cis alpha. Now, I want to say S, but that's going to confuse me a lot. So I'm going to say cis, T cis beta, T cis beta. Okay, now, what does that product look like when I do this? Well, it should, by definition, be that, right? But I actually worked out what cis alpha times cis beta was earlier, didn't I? In proposition 17, it's it's just the sum. Cis alpha plus beta. And considering how we're just asking for the argument of ZW, it's right there. It's alpha plus beta. And yeah, therefore, like, this has to be true. Okay, so I'm convinced by that. I'm convinced about that now. So now how about this? The argument of Z over W is the argument of Z minus the argument of W. Okay. Z is R cis alpha. W is T cis beta. And how to do that? So how do you do that then? Cis alpha over cis beta. No, I mean that's essentially what it's all about. It's about showing that cis alpha over cis beta is equal to probably you have to go back to definitions. Totally wrong. It's supposed to be that. Okay. Then do that. Then that on there. So cos squared beta sine squared beta. And that's just 1 on the denominator. That's just 1 on the denominator. Right, so the numerator is just that now. And so then the question is, does that equal cis alpha minus cis beta? No. There's a minus sign and a plus sign. Minus. Question is, are they the same thing? Okay, so I don't think they're the same. They don't seem the same, is what I'm saying, but right. Put a pin here. Come back to this. Try this one and think of it again afterwards. Right, so they're saying the argument of the conjugate of z is the negative of the argument of z. Well, you can't do that because that's not in the format the way you know what the conjugate looks like precisely. Not yet, anyway. So anyway, first you have to let z be that. Then z bar, by definition, would be that. So the argument of z would be arctangent of b over a. And the argument of z bar would be the arctangent of minus b over a. And yeah, then this is just dependent upon knowing this property about the arctangent function, right? As long as z's not equal to 0. All right, the 14th one. Z times z bar. Okay, so that's a plus bi times a minus bi. The interior, the outside and inside terms cancel out. So we get that there. And that is, of course, no, I mean, that is the modulus of z, but squared. Yeah. It's just, that one's really a simple one, I think. Okay, then come these three beauties right here to do with arithmetic. So like z plus or minus. You know what? I'm going to see if I can carry the plus or minus the whole way through. Maybe I can, maybe I can't, I don't know. This is gonna confuse me, isn't it? But just try anyway. Okay, so okay, so A plus C. No, I've already made a mistake. So A plus minus C. Plus B plus minus D I. That's what that's equal to. And that's equal to A plus minus C minus B. Ooh, brackets. B plus minus D I. And then, what's that? Okay, then we go A minus BI. That minus sign will turn that into a minus plus. So oh my goodness. Okay, in the future, I'm not going to do this. I think, yes. No, darn it, I messed it up. Yes. Okay. Product. Conjugate of product. Okay, I know what the product looks like by now, I hope. So A plus BI times C plus DI. It's AC minus BD. BC plus AD. And we conjugate all of this. And we get this. Now, I'm not going to pretend that I know that this is conjugate Z times conjugate W. So I'm going to be honest. And I'm going to actually do this. Because I really don't like it in proofs when they just go from left to right and they just pretend like they know it all along. Because I just think it's artificial, like it's not real. So, yes, that's going to be A minus BI times C minus DI. And when we do that, we'll get AC minus BD for the real part. Okay. Then minus BC minus AD. And and all of that is times by I for the imaginary part. And then finally, we extract out that minus sign, and we have what we're looking for. Okay, now I believe it. Now I believe it. Quotient. Modulus of quotient is quotient of modulus. Okay. Still not too sure about dividing one complex number by another. Still not like automatic yet. And I know that this has to be conjugated, but just give me a second. Like that. What goes on the bottom here? What goes on the bottom? C minus di. I know that's going to be a c squared. And I know that the outside and inside cancel by design. And that'll be a plus d squared. Okay, got that. And conjugate the whole of this. Okay, so you have to work out the top still. Okay, AC plus BD. That's the real part. BC minus AD. That's the imaginary part. Okay, so the real part is untouched. The imaginary part becomes its negative, so AD minus BC, all over C squared at D squared, and then that times by I. Now, Z bar over W bar. All right, so that there is Z over W, and then bar, the whole lot. And now I've got to do Z bar over W bar. So Z bar is A minus BI. W bar is C minus DI. And I'm still not at the stage where I can just do this totally in my head. I need to write it out. Write it out and then figure it out. C squared plus D squared. That is, let's see, you've got minus BD plus BD. That's my real part. And then AD minus BC. That's my imaginary part. And that looks basically exactly the same once you split the pieces up. Oops. Yep, That looks totally the same, which I like. Okay. Modulus of z bar is modulus of z. Is that true or not? Whoa. And they match exactly. 19 proposition. This one, 19. Modulus of z at w is less than or equal to the modulus of z at the modulus of w. Right. Oh, that's wrong. And wait, is this really the way? Man, this isn't the way to do it. Look at that. How are you going to ever fix that? Polar form. Oh no, because I don't know how to add in polar. I guess that's not the way either. Do I have to appeal to the definitions every single time? I don't think so. Like, how can I make an argument for this? Ooh, that's nice. Yeah, okay, so I'm going to move on from that. Here we go. Leonhard Euler, 1707 to 1783, was a prolific Swiss mathematician. Over 800 papers bear his name. I'll begin again. Leonhard Euler was a prolific Swiss mathematician. Over 800 papers bear his name, and indisputably the greatest mathematician of the 18th century. He made major contributions in many areas of mathematics. Don't know what that was. In many areas of mathematics, but especially in the study of infinite series, and in particular, he determined the sum of the series 1 plus 1 over 4 plus 1 over 9 plus 1 over 16, etc., to be pi squared over 6, the so-called Basel problem. Euler's identity, e to the I theta equals cosine theta plus I sine theta, and in particular, e to the I pi equals -1, can be proved using infinite series for the exponential and trigonometric functions. But Euler's name appears widely throughout pure and applied mathematics. Euler's equation is fundamental in the calculus of variations, which involves problems such as showing the shortest curve between 2 points is a straight line. Euler's theorem in number theory is a generalization of Fermat's little theorem. 3 important centers of a triangle lie on the Euler line. Euler also produced some of the first topological results. He famously showed that it was impossible to traverse the 7 bridges in Königsberg without repetition. In fact, determining more generally which networks or graphs can be traversed. He also showed for a convex polyhedron that V minus E plus F equals 2, where V, E, and F respectively denote the number of vertices, or corners, edges, and faces that the polyhedron has. Both these results depend on shape, e.g., how the points are connected, rather than geometry, e.g., the lengths of the edges. Corollary 19. Suppose that z0 is a root of the degree n polynomial p of z equals an times z to the n, all the way down to a0, where the coefficients ak are real. Then the conjugate z0 bar is also a root of pz. Consequently, p of z can be represented like this, where alpha 1 to alpha r are real roots of pz, q1z to qsz are real quadratic polynomials with conjugate complex roots. In particular, an odd degree real polynomial has at least one real root. And there's the proof. So I guess it doesn't lend itself very well to being read aloud. The fundamental theorem of algebra tells us a polynomial's roots can be found amongst the complex numbers. So the roots of p of z are either real, call these alpha 1 up to alpha r, or come in conjugate complex pairs, call these beta 1 bar, all the way up to beta s bar. Now, z minus beta k times z minus beta k bar is equal to z squared minus beta k plus beta k bar times z plus beta k times beta bar, which is equal to z squared minus 2 times the real part of beta k times z plus beta k modulus squared. If we denote this real quadratic as qk of z, then p of z is this, where n equals r plus 2s from equating the degrees of the polynomials. Note that if n is odd, then r is greater than or equal to 1, and so p of z has at least one real root. All right, let's have a look at the roots of unity. Consider the complex number z. Okay, this is starting to, at this very moment, it's starting to hurt my eyes a little bit. So I'm going to stop there because you've got to look after your eyes more than anything else. All right, so be well, be well.